Welcome to the flock. Let's dive into nuclear fission chain reaction, explained through the application of a nuclear power plant, specifically the one located in Arizona. Stick around to see how you can solve a fission chain reaction just like this one. Now, if we're going to talk about nuclear power, of course the thing we need to reference is, what is it even used for? It's used for our electricity. It's used to keep the lights on in our home. And how much electricity is that really? Let's try and get a baseline for how much energy this truly is using the United States yearly average of 0.47 terawatts. Just how big is a terawatt? Well, we have kilowatt, megawatt, gigawatt, and then we have terawatt. So the fact that the entire United States uses almost 0.5 terawatts is indeed quite a lot of energy. Out of that grand total of energy, how much energy do you think your house uses on a yearly basis, or even a monthly basis? Let's talk about this in reference to one single power plant of interest, Palo Verde Power Plant, located in Arizona. This is literally the only power plant in the entire world that isn't located near a large body of water. It's literally in the middle of the desert. Just how much desert? Nearly 4,000 acres of desert. It has 3 pressurized reactors, and each reactor produces roughly 1.24 gigawatts of energy. In other words, if you add all 3 together, that's a grand total of 3.7 gigawatts of energy. Now, that question I asked you earlier, what is it you think that your home uses? Well, on average, that turns out to be 1.38 kilowatts per month. Remember, in terms of size of wattage, kilo is the smallest, then we have mega, then we have giga, and finally we have terawatts. So your average home in the United States uses the 1.38 kilowatts per month, whereas all 3 of these generators combined creates 3.7 gigawatts. And in the United States, we use just about 0.47 terawatts per year of energy. For size reference then, let's say we had 1 gigawatt. How much would that give us power for? That would supply enough energy for 725,000 homes. Now keep in mind, again, all 3 of these nuclear reactors is 3.7 gigawatts of energy. That's a lot of homes. In fact, that's 35% of the energy production in Arizona. Now, I don't think you're truly understanding the gravity of this situation here. We know that one nuclear reactor from Palo Verde in Arizona produces roughly 1.24 gigawatts of energy. Let's compare this value to other sources of energy. How many windmills would it take to create 1.24 gigawatts of energy? Well, it would take roughly 484 wind turbines to create the same energy. What about solar panels? Well, it would take about 8,066,666 solar panels to create the same amount of energy that one nuclear reactor does. How about people on bicycles? It would take about 6 million people on bicycles to create 1.24 gigawatts of energy. And last but not least, how many hamsters and spinning wheels would it take to create 1.24 gigawatts of energy? Well, it would take about 8,066,666,670 hamsters in spinning wheels to create the energy that one nuclear reactor does. What am I getting at here? It's a lot of freaking energy. So if we're looking at the Palo Verde Power Plant generating station from an aerial bird's eye view, we can see that the 3 nuclear reactors are right behind me, and there's all of this steam coming off of something, coming out of the ground seemingly. That's literally water vapor. Where's the water coming from? We mentioned that it's literally surrounded by 4,000 acres of desert. There's no water to be seen anywhere. And you might be thinking, this is a huge waste of water. Actually, we use wastewater, 20 billion gallons of it trucked in and treated wastewater to literally evaporate out into our atmosphere using the nuclear power plant. And these nuclear reactor containment centers are some of the largest in the world here at Palo Verde Power Plant at 2.6 million feet cubed. Whew! It's basically one of the largest treated wastewater jacuzzis in the world. Well, now that you know what it looks like from the outside, what's going on with the chemistry on the inside of that nuclear power plant? How does this all work? We basically use low energy neutron bombardment, or neutron radiation, for neutrons to bombard uranium nuclei. We take the unstable uranium-235 and we place it underwater. Now, of course, this uranium is in large uranium rods that are placed underwater. These rods can be pulled out of the water or put back into the water to control when the reaction happens. We then bombard the uranium with neutrons. A neutron can come in and bombard this uranium nucleus. When the neutron does come in and bombard the nucleus, it literally makes the whole thing unstable. This causes this larger nucleus to break apart into two smaller nuclei. And when that happens, there's also a bunch of other neutrons that are released, which is really convenient because there's all this other uranium in the uranium rods that all of these new neutrons that have been freed can run into and create a domino effect for this to keep going over and over and over again. Now, every time this happens, there's an enormous amount of heat that's released. This heat causes the water to heat up and go from its liquid phase to its gaseous phase. We basically funnel that steam into a system where it will spin a turbine. When that turbine spins, we generate electricity, and that electricity can be delivered to your home through wires. So the thing that is providing all the energy to your house, yeah, it's essentially just boiling water and capturing the vapor for us to have electricity. Pretty crazy, right? So let's give this a try then in practice. What would that uranium nucleus turn into after the low energy neutron bombardment occurs, i.e. the fission reaction? For each arrow that's coming off of this uranium, we know that that's another neutron that was released. So we'll have to use a little bit of backwards reasoning and rationale here to solve this problem. Looking at our periodic table, we know that element number 56 is barium. So this guy up here should be barium that was created. But what was the other product created? Let's start by figuring out the atomic number of the other product created. We know we had 56 here from 92. So if we subtract those two values, we should have the new atomic number of our other mysterious product. So 92 minus 56 gives us 36. That's the atomic number of our new mysterious element. If we look to our periodic table, we see that element number 36 is krypton. So we're going to write a big Kr there. Now, what's the mass of krypton? We're not going to look to the periodic table for that. We are going to have to reverse rationale using the number of neutrons that got lost in this reaction. Here we know that each neutron contributes 1 to the mass. So here we lost 3. We also know that barium weighs 139 out of the 238. So technically, we lost an entire mass of 139 plus this 3. In other words, a total mass of 142 came out of the 238. So when we subtract 238 minus 142 to be 96 in this case, instead of the 84 that's on the periodic table. Now that we've solved this initial step together, go ahead and pause the video here and see if you can figure out how the neutron bombardment affects here, here, and here, which is demonstrating what's happening inside a nuclear power plant reactor. Ready? Go! All right, let's check your work. And we're done. You should have found those to be your answers for this fission chain reaction. Notice that we still had 2 other neutrons here that were flying off into space to go react with other uranium nuclei. In Arizona, there are some genuine safety concerns and evacuation plans that are in place, or if the worst case scenario were to happen with the Palo Verde Power Plant. So for example, in the first 10-mile radius around the plant, which kind of looks like this from an aerial view, within this radius would be the largest concern for the direct exposure to the radiation given off of, let's say, the Palo Verde Power Plant if it were to explode. So the alpha, gamma, beta, and neutron radiation that would come flying out of that explosion would be most dangerous within this 10-mile radius. Whereas if we zoom out even farther to the 50-mile radius, we can see that that encompasses actually a huge part of the valley as well. Glendale, Peoria, Sun City West, Surprise, and Phoenix metro area even. Within this radius, we're very concerned with the ingestion or the food contamination or water source contamination of all of those alpha particles primarily, but of course also the exposure from beta, gamma, and neutron radiation. Within this radius of 50 miles, if the Palo Verde nuclear power plant were to explode, this would affect just over 2 million people as of the 2010 statistics. Now I realize we are currently in the year 2021, so that was 11 years ago. There is quite a lot of influx, especially from California, into the Phoenix metro area. So there would be way more than 2 million people at this point affected and who would have to evacuate if the worst case scenario did occur and Palo Verde became unstable. If you're interested in the actual evacuation plan from Arizona, please check out that PDF linked in the description below. So why would anyone be so concerned with the safety? Isn't all of this under wraps? Isn't all of this taken care of? Shouldn't we be more advanced in our safety measures now than we ever were? Shouldn't we know what we're doing at this point? Well, people have a right to be concerned. Back in 1986, we had one of the worst nuclear power plant fallouts that ever happened in history. This incident was known as Chernobyl. Should we even be concerned with the safety of our nuclear power plants? Aren't we advanced enough in today's day and age to make sure that everything is safe? Let's travel back in time to 1986. A nuclear reactor experienced an unexpected power surge, and when they tried to help the system from overheating, they essentially made it worse, causing radioactive plumes to drift over the Western Soviet Union and over parts of Europe as well. This was the most disastrous nuclear power plant incident in history, known as Chernobyl. And to this day, the areas in which those explosions happened around the nuclear power plant are essentially nuclear wastelands. Not only that, but the radioactive plumes that drifted over Europe, there are still areas there where I grew up, where you couldn't go pick the wild blueberries from the forest, or you couldn't go mushroom hunting, which is a very fun pastime for anybody that has grown up near a forest, because they're essentially exposed to still radioactive material from that incident in 1986. So do we have a right to be a little concerned? Of course we do, but that's where the politics intercedes with the science. We know that the nuclear power produces a lot of power. Remember, over 8 billion hamsters spinning in wheels would just be one nuclear reactor. So quite a lot of power can be produced from this nuclear power plant. And so long as we can keep our safety measures nice and tight, hopefully we will never experience another Chernobyl incident. In fact, if you're curious about what a nuclear explosion would look like for the area you live in my case, I put in my area in Portsmouth, Virginia, 23703, you could see what the nuclear fallout for a bomb like the W-87 would have for the area I live in. You can see the fireball radius, the heat wave, the shock wave, and where the radiation would be the strongest. Of course, if you're interested, you can always go up in bomb size as well, like the Tsar Bomba. With this one, I would essentially become dust. I would be pulverized in the core of that radiation. And so would 412,509 people be pulverized in that radiation. If you're interested in checking out what a nuclear bomb would do to your area that you live in, find the link for that in the description below. In this lesson, we discussed a real nuclear power plant located in Arizona called Palo Verde. And we discussed the different information basics about that power plant and how it has 3 pressurized nuclear reactors that evaporate off 20 billion gallons of treated wastewater to supply 35% of Arizona's energy. Those 3 nuclear reactors produce roughly 3.7 gigawatts of energy. In other words, there's about 1.24 gigawatts per reactor. And that 1.24 gigawatts is literally equivalent to over 8 billion hamsters spinning on spinning wheels, or hamsters. We demonstrated how nuclear fission is what is occurring inside those nuclear reactors, where neutrons are literally bombarding the nuclei of uranium atoms, causing them to become unstable and break apart even farther to bombard other uranium nuclei, producing a lot of heat, and that heat boils the liquid water into steam, and the steam spins a turbine, giving us electricity. We can control the rate at which that neutron and uranium bombardment occurs by keeping it submerged in water. And when doing calculations or showing a fission pathway, we need to take into account where and how many neutrons were given off from each bombardment, and how in the past, incidents like Chernobyl are what give us those safety concerns to begin with. And now, as promised, from the nuclear chemistry video part 1, the one right before this, here's the answer to the series of decays for uranium-238. And there you have it, the decay of uranium-238. All the way down to lead. Please give this video a giant quacks up, and when you're out of luck in chemistry, subscribe to the duck. Hoping that your understanding of this content is radioactive. And remember to keep it quacky.
No ducks, no glory.